Okay, estimating a population proportion. So the main concepts here in this section are going to be this. The point estimate, which is a sample proportion denoted by p hat, we call this, and that's the best point estimate of the population proportion p. Confidence intervals, we'll use a sample proportion to construct a confidence interval estimate of the true value of a population proportion. And we should know how to construct and interpret such confidence intervals. Sample size, we should know how to find a sample size necessary to estimate a population proportion, right? So, point estimate. It's a single value used to estimate a population parameter. So, the sample proportion p hat, we call it, is the best point estimate of the population proportion p. So it is unbiased estimator, as we found out previously, and p hat targets that population proportion p. Alright, so let's start with an example of just kind of getting the terms kind of focused and realized what they are. So the chapter problem includes a reference for the Gallup poll. It says in which 1,487 adults were surveyed, and 43% of them said that they have a Facebook page. Based on that result, find the best point estimate of the proportion of all adults who have a Facebook page. Well, this question's pretty easy because that 43% there, that's going to be our p hat, because that's what they're saying. We had a sample. We don't know what the overall population proportion is, right? We just have a sample of 1,487, and 43% of them said that they have a Facebook page. So that's our p hat. So it says because the sample proportion is the best point estimate, we conclude that the point estimate of p is 0.43. So we call that p hat. And n is the number of our sample, 1,487. And then q hat would just be 1 minus p hat. Remember, they would just add up to 1. Very similar, because it's very similar to what we've been doing, because it's a probability, right? It's a binomial. All right, so now a confidence interval. Confidence interval would be bounds. They would be bounds on that 0.43, because that's an estimate, right? So now a confidence interval, we want to be sure that we are so confident that we're capturing the true proportion. So we'll create a confidence interval. We saw that 0.43 was our best point estimate of p, but we have no indication how good that estimate is, right? We just know that it does target it. A confidence interval gives us a much better sense of how close our estimate is. So a confidence interval is a range of values used to estimate the true value of a population parameter. So a confidence interval is sometimes abbreviated with CI. So you'll see that in the homework. A confidence interval is the probability of 1 minus alpha, such that 0.95 or 95%, that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. The confidence level is also called degree of confidence or confidence coefficient. We don't really use those as much, but basically we're going to say we're 95% confident that the true population proportion falls within this range. Alright, so we have alpha to show our confidence levels. So if we say we have an alpha of 0.10, that corresponds to a 90% confidence, right? 0.90, 0.05, and 0.01. So example, if you have an alpha of 0.02, you're going to have a 98% confidence level. You're just subtracting that from 1 to get our confidence level. So the alpha gives the confidence level. So let's interpret one. It says we must be careful to interpret confidence intervals correctly. There is a correct interpretation and many different creative incorrect interpretations of the confidence interval. So here we have a confidence interval of 0.405 to 0.455. So this is P. We're saying we believe that P falls within this range. And the correct interpretation of this is we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. So short way, an acceptable way of saying that we were able to select many different random samples of size 1487 and construct a corresponding confidence intervals. 95% of those would contain the population proportion P, the true one. In this correct interpretation, the confidence level 95% refers to the success rate of the process used to estimate the population proportion. So these things are wrong. That's not what we're saying. There's not a 95% chance of getting the true thing. That's not true. And 95% of the samples fall. That's not true. It says we are 95% confident that they will fall in there, but not 95% of them do fall in there. It says this is wrong because the values result from one sample. Okay? So we're going to do this like a lot of times, taking the same sample size over and over and over and over. Okay? Confidence level, the process success rate. A confidence level of 95% tells us the process we are using should, in the long run, result in a confidence interval limits that contain the true population 95% of the time. Suppose that the true proportion of adults with Facebook pages is 0.50. That's the true. See figure 7.1, which shows that 19 out of the 20, or 95% of the confidence intervals, contain that. So here's 20 confidence intervals, and here's our confidence interval, and 19 of them actually contain the true 0.50, where this one did not contain it. So with a 95% confidence, we would expect about 19 out of 20 to do that. So we're going to find that confidence interval of the proportion P. In order to do that, though, we need to know critical values. Critical values are formally defined on the next page here, and they're based on the following observations. When certain requirements are met, the sampling distribution of sampling proportions can be approximated by a normal distribution. A z-score associated with a sample proportion has probability of alpha over 2 of failing in the right tail of the, a z-score associated with a sample proportion has a probability of alpha divided by 2 of falling in the right tail portion over here. The z-score at the boundary of the right tail region is commonly denoted as z sub alpha divided by 2 and is referred to as the critical value because it is on the borderline of separating the z-scores that are significantly high. So we're interested in that value. So you see we got alpha. So you're going to take alpha divided by 2, and then that's going to be this little area here, because you see you have another area over there. So the critical value is the number on the borderline separating the sample statistics that are significantly high or low. The number z sub alpha is a critical value that is a z-score with the property that it is a border that separates the area of alpha over 2 in the right tail of the standard normal distribution. So I know there's getting a lot of words here for stats, but it's not that hard. It just says find the critical value of z sub alpha with a corresponding 95% confidence level. So we want to be 95% that all these are falling in there, right? So alpha would be 1 minus 0.95. So we'd have a 0.05 alpha, right? So now we want alpha divided by 2, though. So we need to split that to find the correct critical value. So if you take 0.05 and divide it by 2, you're going to get 0.025. So you have 97.5% corresponds to the area to the left of value z. So if you put 0.025 here, all the way to the left would be the other 0.975. So there's 0.025 to the right of z. So here's what it looks like. You see the area of 0.025 is over here, 0.025 is over here. If you add them up, you get 5%, or 0.05, which is showing a 95% confidence interval. See, it's going to fall between here, right? These are significantly high and significantly low. So we started out saying our confidence interval is 95%. That is an alpha of 0.05. Divide that by 2 to get the 0.025. And now we know that 9.975 falls to the left the entire way. So we can easily find this z-score. they have a table here showing the kind of the common ones. If you have alpha of 0.10, then you have a 0.05 critical value, right? So 1.645 is the z, and then etc. But if you don't have the table, you can always just use statcrunch. So if I just bring over statcrunch, I go to the calculator normal, because these are just z-scores, right? So we can just leave them as mean 0, standard deviation 1, and then find whatever percent you want, and it'll show you the z-score right here. So if you want, remember it's to the right, 0.025, which was a 95% confidence interval, 0.05, then change this to the right and put 0.025 in there, and you'll get the 1.96. There it is, a 0.05, 95%. If you want a 99% confidence interval, then you need to go in here and put in the 0.005, right? And then you get 2.58 or 575 or whatever they have there. You could round that up, I guess. Okay, 0.005, half of that. So this is how I can just calculate any one. Here I want half of this one. Alpha is 10, so I want 5% over here. 1.645. Okay, so these are called critical values. Critical values. All you're doing is looking at alpha, dividing by 2, looking for that right tail, the right one. Let's go to a homework problem here and try this one here, number 4. It says find the critical value for 89%. Okay, remember 89% is 0.89, so we're talking about an alpha of 0.11, right? 0.11 is our alpha. So I have 0 and 1. 0.11 is our alpha. Well, we want alpha divided by 2. So if it was 0.10, it would be 0.05, but it's not. It's 0.055, right? Because that would be the area to the right. And then we'd get 1.598, or rounding up to 2 decimal places, 1.60. So this confidence interval, you change to an alpha, you divide it by 2, and that's the area. The alpha is that area to the right divided by 2, because then there would be to the left as well. If we did it to the left and we wanted 0.055, we get the negative version, right? So they both add up to the 0.11 in this case. All right, margin of error. When the data from a simple random sample are used to estimate the population proportion P, the difference between the sample proportion P hat and the population proportion P is the error. That's how far you're off. The maximum likely amount of error is the margin of error, okay, denoted by E. There's a probability of 1 minus alpha that the difference between P hat and P is E or less. So it's saying the difference, that margin of error is just going to be E or less. And we have a 95% chance of that happening, or probability of that happening. Okay. The margin of error E is also called the maximum error of the estimate and can be found by multiplying the critical value and the estimated standard deviation of sample proportions shown here. So here's a critical value. We just figured that out. That's that number. For example, the one we just did, right? It would be 1.60. That's the critical value for the 89%. We know P hat, that's point estimate. Q hat, just 1 minus P hat, and then N. So this calculation is not all that bad to find that error. So let's look at creating a confidence interval. Construct a confidence interval and use to estimate the population proportion P. So we got P is the population proportion, P hat, sample proportion, right? N, the number of the sample values, E is our margin of error, and Z alpha sub alpha 2 is the critical value. So the requirements is that we need a simple random sample, which we normally have. The conditions for binomial distributions are usually met, or have to be met. And then we have to have 5 successes and 5 failures. So NP5, NPQ. And this is what the confidence interval looks like. It's just our true population proportion is somewhere in between p hat minus e, so go to the left, and then p hat plus e, where e is our error. You also might see it described as p hat plus or minus e, or in notation as an interval like that. And we usually round off to 3 digits. Alright, so let's look at the procedure and trying it by hand. Verify the requirements. Use technology or the table. I'm going to use technology. Estimate the margin of error. Use that error with p hat to find your limits and then round off. Here we go. A Gallup poll of 1,487 adults showed that 43% of the respondents have Facebook pages. That was a poll of 1,487. That's only one poll. Find the margin of error that corresponds to the 95% confidence interval. Find the 95% confidence interval estimate of the population proportion P. And then based on the results, can we safely conclude that fewer than 50% adults have Facebook pages? Okay, so let's just go with A first. N is 1487, and P hat is 0.43, our point estimate. It's lower than 50% already, and that's what we're estimating the true to be, right? Verify the requirements. It's a random sample. It's a binomial. There's a fixed number of trials. Okay, there's 2 categories, outcome or not. There are at least 5 successes and failures. NPQ is greater than 5, of course, because it's so many for N, right? Or NP and NQ. So A, find the margin of error by hand. Here is the formula. E equals Z sub alpha 2 P hat Q hat divided by N. Put the numbers in, P hat, Q hat, 1 minus P hat, and then 1487. And now we need to find that 196. How do we get that? Well, that was the critical value. And what we're doing here is in A, it says a 95% confidence. So what we do is we need this, and we need to come back over here. If we're doing a 95% confidence, that's 5% in right and left, or 0.25 just in the right. Right? So 1.96, if you round it off to 2 decimal places, 1.96. And that's where the 1.96 is coming from. Remember, the table has that as well. Now we're going to take the calculator, and we're going to just figure this out. So there's a lot going on here. You could put it all in at one time. That's fine. But make sure you know how to work your calculator with correct parentheses and stuff. I'm going to start in the middle and work outwards. So I'm going to do 0.43 times 0.57 and hit enter. That's those two in the top. Then I'm going to divide that by 1487. Okay, that's scientific notation to a really small number. Now I'm going to square root that. So I go square root answer to get that. Then I'm going to multiply that by 1.96. 0.0251 or 252, right? That's what they have here. So that's the error, that's the error, margin of error. All right, let's continue down. Since we have the margin of error, we can find the confidence interval. So the confidence question for B was find the 95% confidence interval of the population proportion P. Well, we have that error, so now we just need P hat, which was the 0.43, and we just need our error here, which is 0.02516636, and we just add it and subtract it. That's all. So 0.43 minus the value I had as my answer in here. There's that one, 0.404836, right? And we'll round it to the 0.405, and then you add it, 0.43 plus 0.455. So this is the confidence interval. Now what does that mean? The results, it says, based on the confidence interval obtained in Part B, it does appear that fewer than 50% of the 50% of the adults have Facebook. because the interval of values from 0.405 to 0.455 is an interval that is completely below the 0.50, the half mark. So the one statement that summarizes the result is this. 43% of adults have Facebook pages. The percentage is based on the Gallup poll of 1487 randomly selected adults in the United States. In theory, 95% of such polls taken, the percentage should differ by no more than 2.5 percentage points in either direction. 2.5 is that 0.025 because we were 95% confident. 2.5% to the left and 2.5% to the right from the percentage that would be found by interviewing the adults. Okay? So we can do this in statcrunch. That was all by hand. We can do this in statcrunch as well. But let's do another one over here in the homework by hand. So use the sample data and confidence levels below to complete these parts. A research institute felt if vulnerable adults identify theft in a poll, n equals 962 and x equals 564, who said yes. So that's how many that said yes. Use a 95% confidence interval. We can use these z-scores if we want in the table, but I just use statcrunch, right? Find the best point estimate. This is for later, for the confidence interval. Find the best point estimate of the population proportion p. All right, we'll look back. What is our estimate here? What percentage of people are doing this, right? Well, we don't have that. It's not given, but it is given that 564 out of 962. 564 out of 962. So 0.586. So about 58.6% of them. That's the p hat. That's our point estimate. That's what we're saying now. Now we're wondering, can we create a confidence interval that includes that, or will it not include that? Okay. So now we identified the margin of error. Remember, the margin of error is this formula right here. We need to get the z sub alpha of 2. So we have a 95% confidence, which was what we had here as well. So we're definitely using the 1.96, right? That comes again from here. All I'm doing is saying I want 0.025 because a 95% confidence interval means 5%. 0.05 is my alpha. Divide by 2. I get 0.025, which corresponds to the 1.96. Again, you're getting a little confused with this. Just hold on to the table that shows you the confidence level with alpha for the critical value. Here we are. 0.05 is a 95% confidence level. So we're using the same thing, 1.96. Now we just need p hat and q hat. Well, p hat is what is right here, 0.586. Q hat is just 1 minus that. 1 minus 0.586. There's q hat. So now we just need n. P hat, q hat divided by n, and n would be the 962. 0.586 times right up here, what did I get? 0.414 equals, divided by n, 962, equals, take the square root of that, and then multiply by the 1.96, which was that critical value. 0.0311. So the error, rounded off to 3 decimal places, is 0.031. Construct the confidence interval. Okay, go back to the point estimate that we had, which was 0.586. Add and subtract 0.031. 0.586 minus 0.031. 0.555. 0.586 minus plus, 0.031. 0.617. That's the confidence interval by hand. We found that the point estimate, the error with the formula, and then we constructed this. And the statement that it corresponds to is one has a 95% confidence that the interval from the lower bound to the upper bound actually does contain the true value of the population proportion. Because look, 0.55 and 0.61 contain the point estimate. So out of 95% of the samples that we take, 95% of them will contain the true, which we don't know what it is, but 95% will contain the true. That's what we're saying. And this one's containing this best point estimate. Okay? Now statcrunch allows us to do this relatively fast. Let's look at that. statcrunch and proportion stats, one sample with summary. With summary. The number of successes is what we have here, 564. Number of observations, 962. The confidence level, 95. Click compute. We see we get the lower limit, 0.555, and the upper limit. So that was pretty fast, right? But how do we get the error and the point estimate? Well, you have to do the point estimate, right? That's just the same thing that we did at the beginning. 564 divided by 962. And then this one now is the middle. Because remember, the error was 0.031 plus that and minus that. So this is the middle of these two, the 0.586. So what I would do with my calculator to find that error would be just to take our point estimate, 0.586, and subtract it from the bottom one, maybe 0.555. 0.031 would be my error because it's 0.031 down and up. So this does it pretty quick. You're welcome to do both ways, but obviously statcrunch is much faster. Alright, let's look at the last part, analyzing polls. Example 3 deals with the typical poll. When analyzing results from polls, consider the following. The sample should be a simple random sample, not an inappropriate sample. The confidence level should be provided. It's often 95%. The sample size should be provided. Except for relatively rare cases, the quality of the poll depends on the sampling method and size, but the size of the population is usually not a factor. Okay? Finding a sample size required to estimate a population. So we want to now find the size we need in order to estimate a population. Because how do we know we're taking 1,000, we're taking 900, we're taking 40? How many do we need? Here are all of our characters. We got them all the same. We know what they all are. So when the estimate p hat is known, when you know what that is, either you figure it out by doing the division like we just did, or they give it to you like 30%, 23%. We use it with p hat and q hat. If they don't give you an estimate, you don't know it, then you use 0.25. So round off rule, if computed sample size n is not a whole number, so when you calculate n after all this, it's not whole, you always round up to the next larger whole number. So for example, if it's 1067.11, you actually need a next person, right? You need 1068 people. Alright, so let's look at an example. When the author was conducting research for this chapter, you can find no information about percentage of adults who make online purchases. Yet the information is extremely important to online stores and brick and mortar as well. If the author were to conduct his own survey, how many adults surveyed need to be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points. So we need to know how many we need to sample. Assume that a recent poll showed 80% of adults make online purchases. So that's, now we know we have a point estimate. Then B is assume we have no prior information. So what they're doing is forcing us to use these formulas in order. We know p hat, we don't know p hat. Solution 1, with a 95% confidence, that's 1.96 for our critical value, right? Alpha is 0.05, divided by 2, you get the 0.025, right? You come in here, if you don't remember how to do it, it's the normal calculator, and 0.025, and that gives us our 1.96. It's in that table. The margin of error is 3%. How do we get the 0.03? They told us. Confident the sample percentage is in error by no more than 3 percentage points, which is the decimal equivalent of 3%, right there, 0.03. Now p hat was in A, 80%, so q hat is 20%. So here, we need to be able to put all those pieces in here to find the n. And we use the calculator to kind of do that. Of course, you got to be careful entering all the information. So z sub alpha divided by 2 is that 1.96 squared times 0.80 times 0.2 divided by 0.3 squared. So 1.96 to the second power. Then I'm going to multiply that by 0.8 times 0.2. Now I'm just going to hit enter before I do divide because I want all that calculated. Divided by, in parentheses, 0.03 to the second power, right? 682.95. That's what they have, but we have to round up. 683. So 683 adults we must survey to be 95, have a 95% confidence interval that we're getting the true population proportion. With no prior knowledge of p hat, we have to use this other formula where we have the 0.25. It's actually a little easier. You just have the 1.96 squared. You just got to know you have to use this one. Then times the 0.25. And then divided by the 0.03 squared. $1,067.11, round up 1,068. Because you have no estimate of what you're doing, you need more people so that you're able to get that true population proportion estimate, right? The true population proportion in your confidence interval. To be 95% confident that our sample percentage is within 3 percentage points of the true percentage for all adults, we should obtain a simple random sample of 1,068 adults, assuming no prior knowledge. By comparing this result to the sample size of 683 found in Part A, we can see that if we have no knowledge of a prior study, a larger sample size is required to achieve the same results as when we have a value of p hat can be estimated. Let's look at one more example if you'd like to. This is the last thing. New York Times article reported that the survey conducted in 2014 included 36,000 adults, with 3.72% of them being regular users of e-cigarettes. So that's a p hat. Because e-cigarette use is relatively new, there is a need to obtain today's usage rate. How many adults must be surveyed now to have a 99% confidence level and a margin of error of 2.5% percentage points are wanted? Complete the parts here. So we want an error of 2.5% or 0.025, right? So assume nothing is known about the rate of among adults. How many do we need? So we don't know. The first question is we don't know. And now we want to know what it is. This is what it was. That's the old one, right? Okay, well, we don't know, so it's this one. We need to find a 99% confidence interval. Delete that. 99% is 0.01. But I need to have the half of that alpha, right? 0.01 divided by 2, 0.005. So I need 2.58. 2.58. 2.58 is going to be the critical value right here, excuse me. So 2.58 to the second power times 0.25 divided by our error. 2.5% is our error, so 0.025 to the second power. 2662, and we round up. 2663. I'm not sure why there's many different answers here. It might be because you're using different types of ways to get the answer, or if you're rounding or not. You might, depending on the rounding you do of your z value here. So if you don't round the critical value, if I take all of this, that might be a difference in our numbers. So we currently have, and it's a perfectly valid answer, 2663. 2663 is right there, okay? So now we're going to be using this formula. P hat is 3.72, and then Q hat would be 1 minus that percentage, right? Okay, so the critical value would be 2.58 squared. Then we'll multiply that times the P hat, 0.0372, times the Q hat. I didn't do that, so 1 minus the 0.0372. Notice how I have parentheses here, so that calculates this. And then divided by the E squared, which is 0.025 squared. 381.4. We should round up to 382. And I think they have that as an answer as well, 382. Does the use of the result from the 2014 survey have much of an effect on sample size? Yes, it does, right? If you have no information, the sample size is huge. If you do have some information, the sample size is much smaller. The result from the 24 dramatically reduces the sample size. Okay, so that's how you're figuring out n. You're just using these formulas and calculating it out on the calculator. Good luck.